Hi everybody, my name is Martin Zimmermann and I'm going to present joint work with Daniel Neider from Max Planck Institute for Software Systems and Patrick Totzke from the University of Liverpool on the synthesis of optimally resilient strategies in pushdown safety games. So the basic problem we are interested in here is the one of reactive synthesis, the automatic generation of a correct by construction system from a given specification. As a toy example, consider the following environment containing on some grid some mountains, some lakes, here are some slippery leaves, and here are two red robots which serve as the antagonists in this setting. And then we have the system we are interested in, which is just another robot, the blue one here. And now the robots can move, say first the blue one, then the red ones each make a move, then the blue one again, and now the red ones, and so on. And now we see that here it's getting a bit close for the blue robot, and at the end it's caught. So one specification you could have for your system, so the blue robot, is to never get caught by the red robots, to survive forever. The way to model such a synthesis problem is to encode the interaction between these two agents, so the two red robots as antagonists and the blue robot as system, in a graph. So we have a graph here. Notice we have two types of vertices. Each vertex encodes the state, the current state of this environment, essentially the positions of the robot and whose turn it is. At the round vertices, it's a system player's turn, so the blue robot makes a move. And at the square vertices, it's the environment's move, so the red robots are moved. And in the following, we will call the system player player 0, so the circle player is player 0, and the square player representing the environment is player 1. Okay, so the graph captures the possible interaction between these two agents. And then we have to specify the winning condition. And here we have a very simple one. We consider safety, saying there are certain bad states, the gray ones here, that should be avoided. So these could, for example, represent that the red robots have caught the blue robot. Okay? And now this is a game graph or an arena. And we play as follows. We place a token at some initial vertex. And now the player who owns this vertex, so player 1 here, moves the token to some successor. Now the token is at a player 0 vertex, so she moves the token to some successor. Let's see here. And then we continue, we use a self loop, and now the token has ended up at the gray vertex, which means this play, this infinite pass through the arena, will be losing for player 0 because we have violated the safety condition to avoid the gray vertices. On the other hand, if the token never visits a gray vertex, then player 0 wins because she has satisfied the safety condition. Okay? Now, what we are interested in is a so-called winning strategy, which is essentially a recipe that tells you, depending on the history the token traversed, so a finite pass through the arena, where to move the token to next when it's on player 0's turn. So for example, at this vertex here it would have been better to say, take the self loop up here. Okay? Use that forever. Never use that one, and then you stay safe because you never visit that gray vertex. And if you have such a winning strategy, this can be easily transformed into an implementation satisfying the system specification. So this would give us a strategy for the robot to never get caught by the other two robots, if there exists such a winning strategy at all. Okay? So reactive synthesis has been studied for roughly 50 years now, and many different variations of the problem have been introduced to model certain desirable aspects of an implementation. And here we are concerned with the question of resilience or robustness. The idea introduced by Dalal, Tabuada, and Neider recently is to add a new type of edge to the graph, to the arena, to model non-antagonistic external influences. These could, for example, be the robot going on this grid cell with the slippery leaves, and then saying, I want to go up, but the slippery leaves letting the robot go to the left, for example. So an action picked by the robot is not executed due to some external influence. Another useful example would be a robot that should pick up an object. It has an actuator, it tries to pick up the object, but it slips out of the actuator, so it doesn't grab reliably. If we would give these external influences to the opponent, so the opponent could control whether the actuator works or not, this would not be right. Because then the opponent could just say, I will never let the actuator work properly. And then the robot cannot satisfy its specification. But this is surely not realistic. You hopefully have actuators that work a bit better. And then it makes sense to model this as a rare event. So the actuator may fail, but this is not the standard case. And now you could try to come up with a stochastic model for the failures of your actuator, but these are very hard to come by. And reliably modeling the behavior might be out of the scope of your approach, and you don't have the right data. So what you can do is you can just add these disturbance edges here and say, okay, it might happen that the action that player 0 picks here, so taking the self loop, is not executed, and instead this disturbance happens and we go to the other state here. And now the question we are interested in is how many disturbances make the system player lose. So, and if you look at this, if we start at a vertex which is one of those that you have to avoid, then you already have lost. So 0 disturbances are necessary to make the system player lose. On the other hand, if we look at this vertex, here 1 disturbance is necessary to make the system player lose, right? Player 1 will always pick the self loop here, and that keeps her safe. As long as no disturbance occurs, we won't visit a gray vertex. But if 1 disturbance occurs, then we get to this gray vertex and we lose. So as long as 0 disturbances occur, player 0 wins, but as soon as 1 occurs, player 1 wins. So this is why we give this vertex here a resilience value of 1. Now you can start arguing about these resilience values. For example, this player 1 vertex also has resilience value 1, because player 1 can move the token from the square vertex to the circle vertex here. And there we know already that the resilience value is 1. Now this vertex here has resilience value 2, because again player 0 will use the self loop here. That keeps her in this vertex unless a disturbance occurs. And then we are at a vertex where we know that with 1 additional occurrence of a disturbance, we get to a bad state. So here we get a 2. Now again, this vertex also has a 2 because player 1 may take this one. And this is how far this reasoning takes us. Turns out that from all other vertices, player 0 can win even if infinitely many disturbances occur. So for example, look at this vertex here. If a disturbance occurs, we go to that vertex and get back here. So player 0 takes a self loop, and sometimes we may get here, but then the token is returned here, and that's all that can happen. And none of these states in this component here is a bad state, okay? So this is why these vertices are able to, from there, player 0 is able to win even if infinitely many disturbances occur. And for technical reasons, we use the resilience value omega plus 1 for this case, okay? And these are the resilience values that occur in this game. So 0, 1, 1, 2, 2, and omega plus 1. And in general, Neider and Tabuada showed 2016 that if you have a finite safety game with n vertices, then the finite resilience values are bounded by n minus 1. So that's the largest finite value you can have. And you can have this infinite value omega plus 1, okay? And furthermore, you can compute the resilience values and an optimally resilient strategy, both in polynomial time. Okay, so if you just have a safety condition, then you can determine resilience values and an optimally resilient strategy, one that is most resilient against failures. Let me, before I continue, quickly comment on why we call this value omega plus 1. So if you look at this, you have here the finite ordinals, and then you have omega plus 1. So the question is, what about omega? And it turns out that if you have a different type of winning condition, so for example, a reachability condition or a parity condition, then you may have vertices with resilience value omega. It's just that in the special case of safety conditions, you don't have an omega. Okay? So if you go to infinite arenas or to more expressive winning conditions, you may also have an omega. But for our talk here, the omega is not that important. Okay, and as already alluded to, we are interested in systems with infinite state spaces, and in particular with finitely representable infinite state space systems. Since at the end of the day, we still want to solve algorithmic problems, and then we need a finite representation for the input. And one of the standard classes to consider here are configuration graphs of pushdown automata. So a pushdown automaton has configurations, essentially a pair of a state and a stack content. And these can be changed according to the transition rules. And this gives rise to an infinite graph. Okay? And this is a simple class of finitely representable infinite graphs where many interesting problems are still decidable. So here I have an example. I have just a single stack symbol, call it A, and the stack bottom symbol. And I have three states, the initial state Qi, Q1, and Q2. And what's going on is you can push A's on the stack in Qi, going up this path here. Then at any time you can change into state Q1 without manipulating the stack content. And then you can pop an A with a disturbance transition, or you can use a self loop here. Okay, and then once the stack is empty in state Q1, you can go to state Q2, which is a bad one. So the way this works is membership of vertices to player 0 or player 1 depends on just the state, not the stack content. And similarly, membership in the bad states only depends on the control state and not on the stack content. Okay. And in fact, this is a special type of pushdown automaton because it only has one stack symbol beside the stack bottom symbol. These are so-called one counter automata because the stack essentially serves as a counter that can be incremented or decremented. It's a unary encoding of a counter with unbounded domain. And importantly, you can still test the stack for emptiness. Okay? So this is a restriction of the general pushdown automata graph model. And we are interested in games with disturbances with safety conditions on such graphs. So let's have a look at the resilience values in this graph here. The bad state that is to be avoided has again value 0. This one has value 0 as well because you only have one edge leading you there. And then you have this chain of increasing resilience values 1, 2, 3, 4 because play 0 will try to use these self loops, keeping you away from the gray vertex. But every disturbance takes you one step closer to that vertex, right? So here, one disturbance edge is enough to make you lose. Here it's 2, here it's 3, and so on. On the other hand, up here, every vertex has value omega plus 1, because player 0 can just stay in this state qi forever, increase the stack forever. There's no reason to go down here. Okay? So what this means is that we have one counter graph where all possible finite resilience values are realized. So there's no upper bound on the finite resilience values in a pushdown graph, not even in a one counter graph. Okay? So in general, what we have shown is the following. You can have all finite values, you can have omega plus 1, but you still cannot have omega as a resilience value in a pushdown safety game. And the reason for that is intuitively that pushdown safety games are finitely branching. As soon as you have a class of graphs that has infinite branching, then you can have value omega as well. And furthermore, we have shown that optimally resilient strategies always exist in pushdown safety games. So computing them is now a bit harder, just as in computing the resilience values is harder because the graph is infinite, but at least we know that these optimal strategies always exist. Okay? And again, this is not true if you allow infinite branching. Then you might be in a situation where an optimally resilient strategy does not exist. Okay, and now what our goal is to compute the resilience value of the initial vertex and a strategy that is optimally resilient from this initial vertex. Not necessarily from other vertices, but from this initial vertex, it is optimally resilient. And for this, we first collect some building blocks to build later an algorithm. And these building blocks are concerned with checking whether the initial vertex has certain resilience values. Remember that the possible ones we have to check for are omega plus 1 or finite ones. Okay? So the first lemma tells us that you can, in exponential time, check whether the initial vertex of a pushdown safety game has resilience value omega plus 1. Okay, and the complexity improves to p-space if we consider one counter safety games. And these results are obtained by essentially removing the disturbance edges and giving them to the opponents, while at the same time controlling how many disturbances can occur. Okay, so let me continue. The second result shows that we can also check finite values. So we can check for a given pushdown safety game and some natural number k, encoded in binary, whether the resilience value is equal to k, the resilience value of the initial vertex again. And this problem is in doubly exponential time and in x space for one counter safety games. And the issue here is that we have to hardcode the k essentially, which makes the problem much harder. Okay? And with these building blocks, we can actually already derive a very naive algorithm for computing the resilience value of the initial vertex, and also an optimally resilient strategy from that initial vertex. What we do is the following. Remember, the value is either finite or omega plus 1. So we first check whether it's omega plus 1. This we can do, we have seen. And if it's not omega plus 1, then it has to be some finite value, so we just do exhaustive search. We check for every k whether the value is equal to k, If it is, we return that k, otherwise we increase the k and search again, okay? And we know this algorithm has to terminate, right? But we have a priori no upper bound on the running time, because the running time depends on the resilience value of the initial vertex. And if that would be unbounded, then the running time of that algorithm would also be unbounded. But luckily, it is not. While the resilience values in a pushdown graph or arena can be unbounded, one can bound the resilience value of the initial vertex. Remember, in our example, the resilience value grew with the stack height. And this is true in general. You can show that the initial vertex can only have a bounded resilience value if it is finite. So here is the exact bound. I don't want to go into too many details how you derive that. Please have a look at the paper if you're interested. You have to combine quite a few techniques to get this bound. But what we obtain in the end is the following lemma. If the resilience value of the initial vertex is not omega plus 1, so it's not infinite, then it is actually bounded by this bound B of P, where P is the automaton underlying G. And if you just look at this, you will see that this bound is doubly exponential. Okay, so it's large, but it's still elementary. And now we can improve our algorithm because we have a finite search space now. So what we get is we first check whether the value is omega plus 1. If it is, we return omega plus 1. And otherwise, we just search from k equals 0 up to this bound BP and check whether the resilience value is equal to that k. And by our previous lemma, we know that it has to be one of those finitely many values, doubly exponentially many values to be precise. Okay, and what we obtain by relying on the lemmas we had on the previous slides is the following. We get a triply exponential running time, because in the worst case we have to encode a doubly exponential k, and this gives us this upper bound on the running time. And what we get is an algorithm that computes for the initial vertex its resilience value, and as a byproduct returns a strategy that realizes this resilience value from the initial vertex. Okay, so it's locally optimal. For one-counter systems, remember that we had slightly lower complexities, so this would yield something naively like a doubly exponential space algorithm. But with a lot of more effort, we will actually show that the problem can be solved in polynomial space if you have a one-counter safety game. You can determine the resilience value of the initial vertex in a one-counter safety game in polynomial space. So that's quite an improvement over the naive result. And this only works because we have, in this case, an exponential upper bound on the resilience value. So it's a bit smaller than in the general case. And with that and some clever tricks from the literature, you can show that you can determine the resilience value. But crucially, we do not yet know whether you can also compute a strategy in polynomial space. Okay, so let me conclude by just mentioning what else is in the paper. So we have an outlook on the computation of resilience strategies in pushdown reachability games and other more interesting winning conditions. In particular, as I already mentioned, new resilience values appear there, the omega. We have a new result on optimal strategies in one-counter reachability games without disturbance edges. So there are some connections to previous work. And we have lower bounds on the computational complexity and on the resilience values of the initial vertex. So remember the key upper bound. This is tight, both for pushdown games and for one-counter games. So let me conclude by briefly mentioning open problems that we are working on. We are looking at an extension to more expressive winning conditions. We are currently trying to improve the complexity bounds for pushdown safety games via saturation algorithms, in particular trying to bring down the triply exponential running time, which we conjecture to be not optimal. And we try to compute the optimally resilient strategies for one-counter safety games in polynomial space. So this missing piece we had in the improved result for one-counter games. Thank you for watching. If you have any questions, please feel free to contact us during the Q&A session of MFCS. And after the conference, just feel free to shoot us an email. The email addresses are on these slides. Thanks.